and also in the class you talked about metal that is inducing helicity in the peptide chain. Okay, so although in the assignment thing we had D10 system, Hg2 and cadmium 2, so anyway there is no DD transition possible. But for example, if we had cobalt 2 or a D7 system where DD transition from the metal is possible, so in that case is it possible that after inducing helicity into the peptide chain, there is some synergistic relation and that helicity is being induced back into the metal, and one metal transition DD transition becomes chiral, or we see that
Yes,
in CD spectroscopy?
yes, we can do that. So what happens that if the metal is binding, metal is also going to see the effect of the chirality coming from the ligand background. That means the peptide or the protein in this aspect. So what happens that it depends on the metal, what kind of transition they are actually having at that moment. If it is having only LMC, right down in the case of this mercury 2 or cadmium 2, where the D transitions are kind of turned off because they're all D10 system. So over there, the LMCT bands become CD active. Okay. And in certain cases, if you go to the actual first row transition elements, starting from chromium to copper, so these are the elements that actually show very good transitions in the DD band, and all of them generally become CD active when it is actually interacting very closely to the ligand environment, which is actually chiral in nature. Okay, so they will be chiral. So for an example, if you take, you have gone through probably in the first part of this course, some metal complexes which can be optically active, like say ethylene diamine, if you take as a ligand, and this bidentate ligand, if you put 3 of them and bind a transition element, so it will nicely form either the delta or the lambda isomer. Now the question comes, how do I differentiate between lambda and delta isomer? So what you can do, you can actually do a CD spectroscopy. And depending what metal you are using, if it is a first row transition element which may have some DD transition, so you can see some of the DD transition band will be CD active after the interaction with the ethylene diamine. And you will only see those bands only when it is actually totally optically active. For an example, if you put ethylene diamine and 2 of them, and so let me just draw the structure over here. So for an example, if you are saying you are working with a molecule like this, and this is the ethylene diamine system. So this molecule is optically inactive, right? Because it already, you can explain it has a sigma. Somebody is very sleepy. Okay. So, but if you put 3 ethylene diamine over here like this, now this molecule is optically active. Okay, you can have also draw the mirror image of that, of this molecule. And now if you try to differentiate this molecule, how I can differentiate it? So one thing is that you can have the crystallographic structure of that, which is not very easy to get. The other thing you can do, you can take the CD spectra for both of them. And when you're doing the CD spectra of both these molecules, you can actually looking into this metal-based ligand transition. It can be LMCT bands, because this nitrogen to metal, you'd get a LMCT band depending on the oxidation state of the metal. Generally +2 onward, they show the LMCT band. Or you can also see the DD transition band if this metal is a first row transition based elements, which actually has a very distinct DD transition band. So either of them will show a CD spectra. And generally, when we are actually looking into the CD spectra of this molecule, let's say I'm just drawing the CD spectra over here. So over here, what I am going to see, say actually a band like this for one of them, and the other isomer will show exactly the opposite one. Okay, so from there, we can actually find out whether this is actually CD active or not. Okay, and that means whether it is chirally active, it is chiral or not. Okay, so you can actually use those kind of molecules. Does it answer your question, Rajeshwari?
Yes, so basically this synergistic inducing is
Yes.
possible.
Yes, yes, yes.
Okay.
It's possible. Okay.
Thank you.
Okay. Okay, so any more question? Okay, if not, we'll start the Mossbauer spectroscopy. So as we are discussing last day, one of the first thing I wanted to again clarify that when we talk about Mossbauer spectroscopy, the first thing we actually have to understand what is the energy state we are changing. Okay, so as I'm discussing yesterday, so let me just write down the ground state of nuclear state or excited state of the nuclear state. Okay, and I was using that I equal to half, keeping iron 57 in mind because that is the most common system we are using, but it can be any particular combination. Okay, and over there, what happens that this I equal to half is the ground state, I equal to 3/2 is the excited state. That is for the nuclear state, the nuclear combination of the protons and neutrons. That is in the question. Now, what happens that if we actually put a magnetic field over there, this I is going to split up. Okay, and this is going to split up in plus half and minus half. That is when I put the magnetic field. So now there is a possibility that over here, if I give the particular electromagnetic radiation which matches this particular energy gap over here, so I'm writing it as E01. So if this matches, I will see a transition between this plus half to minus half. But what is actually changing over here? It is the nuclear spin. Okay, it is only the nuclear spin it is changing. It is nuclear spin which is actually flipping from plus half to minus half. And why this plus half and minus half are different? That is because of the presence of the magnetic field. If I turn off the magnetic field, I won't see this difference and I won't see any signal. But over here, I'm going to see the signal only because of the flipping of the nuclear spin. So when I'm talking about this particular state over here, what I'm talking about is the change in the nuclear spin state in presence of a magnetic field. And that is the region of NMR, nuclear magnetic resonance. Okay. And then there's also possibility that I give enough energy so that I can modify this I equal to half ground state and let it go to an excited state to 3/2. So it actually changes from I half to I 3/2. Over here, what is actually changing? The overall distribution of the neutrons and protons, how they're combining over there. Okay, this I equal to half becomes I equal to 3/2. Okay, so over there, the whole nuclear state is changing. It's not only the spin state, it is the nuclear state is changing. This is the nuclear state is changing over here. And this is known as Mossbauer spectroscopy. So first, you have to understand that what is the difference between NMR and Mossbauer spectroscopy, because both of them are connected to the nuclear state. That means the state connected to the nucleus. But what exactly is changing? In NMR, I'm changing only the nuclear spin state, plus half or minus half, something like that. Whereas the nuclear state is from half to 3/2. Okay. So now over there, if I put the magnetic field, this excited state will also split up in 4 lines. Plus 3/2, plus half, minus half, minus 3/2. And over there, you can also see changes. Okay. And that will be only NMR over there also. So over there, you can see that NMR is connected only to the same nuclear state. There is no internuclear state change. So the half from this ground state is not going to the half to the excited state. No. In NMR, they remain in the same nuclear state. Either belongs to half or belongs to 3/2. Okay, they don't interchange in between different states. So that is the big difference between NMR and Mossberg spectroscopy. Okay, and in NMR, all of you know what is the change in the spin state allowed? Anyone? What is the delta S? Is plus minus 1. Okay, that is the spin state you change. That is the spin state. Whereas my I, delta I remains 0 over there in the NMR. But over here in Mossberg, delta I is not equal to 0. Okay, so that is the big difference between Mossberg and NMR spectra. Anybody has any question on that? If you understand, when I'm doing a Mossberg spectroscopy, I'm actually changing the nuclear state. Okay, not the just nuclear spin state. Anybody agrees? Any doubt? Please let me know. This is very important. Okay, if not, let's go forward and try to understand what is the energy I'm talking about. So over here, I am going to draw a scale and try to tell you what kind of the energy we are actually talking about. So over here, I'm drawing the scale. In this part is the energy is increasing. So on the left-hand side is the low energy. As I'm moving towards most to the right-hand side, I'm increasing the energy. So what is the lowest particular energy transformation is possible? The lowest one possible is the translation energy. So generally it is so low that we generally don't look into that as a spectroscope. After that, the lowest one, we can actually measure it properly and look into it. It is actually the NMR. So that means if I put the magnetic field, and in presence of magnetic field, a nuclear spin state is actually dividing in plus half and minus half, and a radiation can bring the change between from plus half to minus half. The nuclear spin state can flip. That is happening in the NMR. And what kind of frequency I'm talking about, what kind of electromagnetic radiation I'm talking about, that is actually radio frequency. Okay, the same frequency as our radios actually work. So that happens for the NMR spectroscopy. Okay, in NMR spectroscopy, we use radio frequency. And just to give you an idea, what is the energy scale for that? The energy scale for that is less than 10 to the power minus 5 electron volt. Electron volt is a unit of energy, and it is less than it is close to 1 microvolt or something, less than 10 to the minus 5 electron volt. So very minimal energy required to induce a change in the nuclear spin state. That is happening in the NMR. So what is the next in goal? The next one actually comes microwave. Microwave energy. So what kind of change the microwave can bring? Microwave can bring the change in the rotational energy. Okay, how the molecules rotate. Okay, and depending on that, what is actually happening. So if you are going to do rotational spectroscopy, then you are actually going to do microwave. Okay, what else we can use with microwave? Anyone? Yes, yeah, you can do also EPR over there. Okay, and how this EPR, which is actually a change in the electron spin state, is connected to microwave, which is a space for rotational spectroscopy. Can anyone explain? Anyone who is taking Professor G.K. Lahiri's class?
Because its mass is less than.
Okay, so how the mass is connected?
It's inversely proportional to.
Okay, mass is connected to what?
Energies are inversely proportional to the energy difference.
Okay, it is close, but not exactly talking the right thing. It is fine for now. So it is actually the difference. So over there, we are talking about the nuclear spin state. Over here, I'm talking about the electron spin state. And over there, if I put a magnetic field again, they are going to differentiate. Over here, it is minus half at the bottom, plus half at the top. It is exactly opposite to the nuclear spin state, especially proton, because the nuclear of a, the proton and electron has an opposite charge.